Imagine this. You walk into a room, could be your office, could be home, maybe even a library or a shop. Everything looks fine, right? Feels okay. But what about the air? The stuff you're breathing in right now, we don't really think about it much, do we? Is it actually clean? Is it good for you? Or is it maybe subtly working against you? We focus so much on what we see, but what we breathe. Arguably, that's the most critical part of any indoor space. Okay, let's unpack this a bit. Today, we're taking a real deep dive into that invisible world. Specifically, we're looking at the fundamental air quality requirements, the ones outlined in the latest LED V5 standards for new construction. Think of this as, I guess, your essential blueprint, a shortcut to understanding how modern buildings are actually designed to keep us healthy. We're talking about the air we inhale, the spaces we spend our time in. These aren't just suggestions, they're real standards shaping our buildings.
And what's really fascinating here, I think, is how these standards show a significant evolution, a real shift. It's moving way beyond just, basic comfort, making sure a room isn't too stuffy. That's old news. Instead, the focus pivots quite profoundly towards prioritizing occupant health and overall well-being. We'll be digging into the science behind it and also the very meticulous, detailed requirements, the ones that guarantee the air isn't just good enough. The genuinely above-average quality. It's really about designing health into the building itself, right from the start, not just as an afterthought.
Absolutely. And this deep dive, it's really tailor-made for you listening. Maybe you're just curious about the air in your own home, what's really going on there. Or perhaps you're actually involved in building design, construction, maybe facility management, or maybe you just want to be informed about something as basic, as fundamental as the air you breathe constantly. Every single day. It's about empowering you with crucial knowledge. And hey, if you find this stuff as fascinating as we do, exploring these kind of hidden worlds, make sure you hit that subscribe button right now, join our community, hear more about how the world around us is being shaped, hopefully for the better.
So, let's kick things off, not with the super technical bits yet, but maybe with a foundation, the intent. Why are these standards here? And what's this initial investigation step all about? Before anyone even thinks about ducts or filters, what's the core philosophy driving this whole fundamental air quality section in LEV5? Why is it so critical, like a mandatory prerequisite?
Yeah, that raises a really important question. Why fundamental air quality? And why push for above average? Why not just acceptable? The intent, well, it's crystal clear, and I think profoundly important. It's a direct, uncompromising focus on occupant health and well-being, period. And this isn't just about preventing obvious things like, coughing or sneezing fits in the office. It goes much deeper. It's a clear recognition that indoor air quality, IAQ as we call it, has this far-reaching direct impact on everything. From our basic respiratory health, think allergies, asthma severity, right through to our cognitive functions, which is fascinating. It affects our ability to focus, to concentrate, how well we retain information, even our mood, our general sense of energy. We've really moved light years past the old idea that a building just needs to, stand up straight and look decent. The modern imperative, really, is that it must be a healthy place, a life-affirming environment. And that means going way beyond just meeting the bare minimum legal codes or what used to be considered acceptable by older, less demanding standards. Instead, LED V5 is setting a much higher bar. It's a challenge, really, to designers and builders. Think proactively about health. Consider things like fine particulate matter, those nasty VOCs, volatile organic compounds, maybe even infectious aerosols. Thinking about all that long before anyone even sets foot in the finished building.
Okay, so if a building gets this AD5 certification and it hits that above average air quality mark, what does that actually mean for me, for the everyday person working there or living there, or maybe their kids learning in that school? Is it something you'd actually notice? Or is it more subtle? Like, what's the real world benefit besides the plaque on the wall?
That's the crucial question, isn't it?
Yeah.
For the everyday person, it translates into a truly proactive approach to their health
Yeah.
and their daily experience. Imagine walking into an office where you're just far less likely to hit that awful mid-afternoon slump. You know that feeling,
Oh, I know it well.
that vague sluggishness.
Yeah.
Often that can be linked directly to poor indoor air, CO2 buildup, lack of fresh air. Or picture a classroom where students genuinely concentrate better. Where teachers maybe report fewer allergy flare-ups.
Yeah.
Think about a shop where both the customers and the staff just feel more energized. Or a home where the air actually helps you get a restful night's sleep, contributes to your vitality. It's not just about avoiding discomfort anymore. It's really about fostering thriving. And this proactive stance, well, it translates to tangible things. A reduced likelihood of allergy and asthma symptoms flaring up. Potentially fewer sick days, simply because there's less airborne pathogen transmission.
Wow.
Enhanced productivity, naturally, because of that better cognitive function we talked about. And just an overall better sense of comfort and well-being. This isn't some tiny, subtle shift. It can be genuinely transformative for people's daily lives. It's moving away from being reactive,
Hmm.
fixing problems after they pop up, to being preventative, embedding health right into the design, the whole operational philosophy. From day one, it's about designing buildings that are, in a very real sense, active promoters of our physical and mental health.
Okay, this next part really grabs my attention. It sounds incredibly insightful. Before a single brick is laid, you're saying, before the architects even finish their sketches, buildings now need to look outside their own walls. What exactly is involved in this initial investigation of outdoor air quality? You mentioned ASHRAE Standard 62.1 2022, sections 4.1 to 4.3. This sounds like such a basic, fundamental first step, but one that maybe gets overlooked too often.
Yeah, what's truly fascinating here is this explicit acknowledgement, this understanding that indoor air quality doesn't exist in some kind of perfect, isolated bubble. It just doesn't. You absolutely cannot effectively design for excellent indoor air without a deep, almost granular understanding of the outdoor air it's going to be pulling in. Think of it like this. The building's ventilation system, it's basically the lungs of the building, right?
Right.
Constantly drawing air from its immediate surroundings. So if that outdoor air is already loaded with pollutants, well, your indoor air quality is going to be compromised from the start, unless, of course, you implement significant, precisely targeted measures, meticulously designed and put in place. ASHRE Standard 62.1 2022 provides the essential framework for this initial but utterly critical investigation. It requires the project teams to really dig in, understand several key things about the local and even regional environment. This includes investigating regional pollutants, maybe understanding the impact from big industrial zones miles away or large-scale farming or even haze drifting in from distant wildfires. It also demands a deep dive into local sources. Things like, are you near a busy highway? Under a flight path? Near construction sites? What about emissions from buildings right next door? And importantly, it explicitly requires considering seasonal variations. That's key. So anticipating higher pollen counts in the spring, understanding maybe increased smog levels during summer heat waves, factoring in potential wildfire smoke events if you're in a prone area. All this information that's gathered, it directly, fundamentally influences the design decisions that follow massively. For instance, it dictates where you should strategically place the building's fresh air intakes. You want to avoid those local pollution hotspots, right?
Makes sense.
And it determines the specific types and levels of filtration needed. You need to properly clean that incoming outdoor air before it gets circulated inside.
Okay, it totally makes sense to look outside, but why is this step so crucial? Couldn't you just, I don't know, install a really powerful, super high-efficiency filter system regardless of what's outside, and just assume it'll catch everything? Why go through all the trouble of this detailed, upfront investigation?
That's a really perceptive question. And the answer really boils down to both effectiveness and efficiency. It's about both. It's crucial because it allows for a truly tailored design, optimized, and ultimately much more effective than just a generic kind of one-size-fits-all approach. Think about it. If you're building right next to a major 8-lane highway,
Yeah.
with absolute certainty, you'll be dealing with higher levels of fine particulate matter, nitrogen oxides, all those vehicle-related nasties. Or if your site is near, say, a petrochemical plant, you might have a very specific mix of VOCs to worry about. Without that specific site-based knowledge, you could easily undersize your filtration system. Or you might accidentally place your air intakes in the worst possible spot, pulling in even more pollution. Or maybe you fail to account for specific seasonal issues like intense pollen seasons that could just overwhelm a generic system. For example, a building in a dense city center is going to need seriously robust particulate filtration for traffic emissions, urban dust. But contrast that with a project in a rural area. It's pristine, right? But maybe it needs specialized filtration for agricultural dust, or specific local allergens, or even that intermittent wildfire smoke if it's in, say, California or the Rockies. So this upfront investigation, it isn't just about being thorough for the sake of it. It actually saves significant energy, resources, and operational costs down the line, because it ensures the system is perfectly matched to its unique environment. You avoid over-engineering, which wastes energy, and you avoid under-engineering, which, well, compromises health. So for you, the listener, what this means is the air you breathe inside these LEED-certified buildings, it's been proactively considered within the precise context of your specific location, not just some generic baseline. It's about making sure the building is a genuine sanctuary, thoughtfully designed to tackle the specific air quality challenges right outside its doors.
That's a really powerful explanation of the why. Okay, let's shift gears now. Let's move into the actual solutions, the building's own operating system for air. We're moving into what the outline calls the core system, specifically ventilation and filtration design for the general spaces inside. So once we know what's outside, how do we effectively bring that air in? And maybe more importantly, how do we manage its quality inside? Our source mentions meeting ASHRE standard 62.1 2022 again, sections 5 and 6 this time, and it offers a few different ways to do it. The ventilation rate procedure, the IAQ procedure, or the natural ventilation procedure. Can you break those down for us? What are they, and maybe when would a designer pick one over the others?
Okay, yeah. If we connect this back to that bigger picture of indoor health, ventilation is absolutely fundamental, foundational. It's literally how we dilute and physically remove all those indoor contaminants we generate ourselves. Bioeffluents, CO2 from breathing, off-gassing from furniture, cleaning products, cooking fumes, maybe even virus particles. You think of it as the building's respiratory system, constantly exhaling the stale, potentially polluted indoor air and inhaling fresh, hopefully cleaner, outdoor air. And ASHRAE 62.1 2022, that's the global benchmark. It's the gold standard, really, for setting minimum ventilation rates and defining what acceptable indoor air quality looks like. So the first procedure, and often the most straightforward and most common one you'll see, that's the ventilation rate procedure. This is what we call a prescriptive approach, meaning that the standard provides very clear, specific formulas and tables. You use these to calculate the exact amount of outdoor air required for a specific space. The calculations are typically based on two main things: how many people you expect in the space, and the total floor area of that space.
Right, simple inputs.
Relatively simple, yes. So for example, designing a busy open-plan office. The team would calculate how much fresh air, and we measure this in units like CFM, cubic feet per minute, or L's, liters per second, is needed per person and per square foot of floor space. This ensures there's a consistent, adequate dilution of those common indoor pollutants. It provides a pretty robust, often quite conservative, baseline of fresh air for everyone inside. It's reliable, and it's relatively easy to verify if it's working. Then moving to something a bit more, let's say, nuanced, we have the IAQ procedure. That stands for Indoor Air Quality Procedure. This one is more performance-based. It's often a more sophisticated strategy. What it allows designers to do is actually reduce the amount of outdoor air they need to bring in. If, and this is a big if the project team can conclusively prove they're achieving and maintaining exceptional indoor air quality using other methods.
Oh, okay. Like what other methods?
Well, things like deploying really advanced high-efficiency filtration systems, maybe incorporating specialized air cleaning technologies, UVC lights perhaps, or photocatalytic oxidation systems, or even implementing continuous real-time monitoring of specific indoor air pollutants, using sensors to actually demonstrate that contaminant levels are being kept consistently very, very low. This procedure definitely offers more flexibility, and it can lead to significant energy savings, because you're not spending as much energy heating or cooling huge volumes of outdoor air.
Right, that makes sense.
But the trade-off is it demands a much more rigorous design process up front, usually a higher initial investment in those advanced systems. And often it requires continuous verification, ongoing commissioning, to make sure it keeps working effectively over time. So it's typically chosen for, high-performance buildings with really ambitious energy efficiency goals, where the owners are willing to invest in more sophisticated, data-driven solutions for air quality. And finally, there's the natural ventilation procedure. Now, this might sound appealingly simple, right? Just open the windows.
Yeah, that's what I was thinking.
But actually, to meet the standard, it involves quite strict, detailed, and surprisingly sophisticated requirements. It has to be genuinely effective, reliable, and consistent. It's far more complex than just hoping for a nice breeze. This procedure often involves meticulous analysis, looking at prevailing wind patterns, the precise orientation of the building on the site, the design and operability of windows and vents, even the strategic use of architectural features, maybe an atrium, a courtyard, specific types of windows, all designed to consistently harness and direct outdoor airflow through the spaces where people actually are.
Wow, okay, so it's engineered natural flow.
Exactly. For a naturally ventilated space to actually meet the AAQG standard, it has to definitively demonstrate, often using advanced simulation tools like CFD, computational fluid dynamics modeling.
CFD, right.
It has to show it can provide adequate and consistent outdoor air distribution across all occupied areas. And not just on a perfect day, but for a significant portion of the year. And critically, it has to achieve this without messing up thermal comfort, without creating awful drafts, and without inadvertently pulling in excessive outdoor pollutants. CFD modeling, for instance, lets designers visualize those complex air movement patterns inside a building before it's built. See where the air goes, identify potential dead spots where air might stagnate, or areas with insufficient ventilation.
That is a fantastic breakdown, really clear. It shows it's definitely not a one-size-fits-all situation. So thinking about a new project, what are the main things, the drivers, that would push a design team towards one of these procedures over the others? Are there specific building types, maybe certain climates, or even just budget realities that make one option the clear winner in certain situations?
You've hit on precisely the right point there. It's rarely about finding the single best option overall. It's about finding the most appropriate strategy for that specific context. The choice really hinges on a careful balancing act. You're weighing several factors. What are the project's energy efficiency goals? What kind of building is it, and what happens inside? What's the local climate like? How good or bad is the outdoor air quality at that specific site? And of course, what's the project budget? What are the capabilities for ongoing operation and maintenance? The ventilation rate procedure. It's often favored for its robustness, its reliability, its relative simplicity. Great for typical commercial buildings, schools, hospitals, places like that. It gives you that straightforward, verifiable baseline, widely accepted.
It's a safe bet, maybe.
In many ways, yes, dependable. Now, the IAQ procedure. That requires more upfront investment, more ongoing monitoring, but it's typically chosen for those cutting-edge, high-performance buildings, ones with really aggressive energy targets, because the energy savings you get from conditioning less outdoor air. That can often pay back the higher initial cost of the advanced air cleaning systems over time. It's for projects ready to embrace a more precise, data-driven approach. And natural ventilation, well, when designed correctly, it's undeniably the most energy efficient. And often, it provides the most appealing environment for people, that connection to the outdoors.
Yeah,
Now, remember,
definitely.
its feasibility is hugely dependent on the climate. It really excels in milder climates where outdoor temperatures are comfortable for a good chunk of the year. And crucially, where outdoor air pollution levels are consistently low.
Yeah.
You absolutely wouldn't want to rely only on natural ventilation in, say, Phoenix in August or maybe downtown Beijing during a smog event. It would just compromise comfort and pull in pollutants.
Right, bad idea.
So the beauty of the ASHRE standard is really its flexibility. It empowers the project teams to look at all these factors and select, then meticulously implement, the strategy that makes the most sense for their unique situation. And just to quickly clarify for listeners, when we throw around terms like CFM cubic feet per minute or ILS liters per second, we're literally talking about the volume of air moving through the system, how much air is being exchanged over time.
Got it. Like lung capacity for the building.
Exactly. A higher CFM means more air exchange, ensuring that constant fresh supply in your space.
Okay, now this is where it gets really interesting for, well, probably everyone listening who worries about airborne particles. Dust, allergens, bacteria, even viruses. Our source material details several options for filtration. We hear about MRV ratings, these ISO standards, even in-room systems. What are the key requirements for the main central HVAC systems when it comes to filtration? And how do all these different standards work together to make the indoor air healthier for us?
Yeah, this raises that crucial question. Okay, we're bringing air in, but how do we make sure it's genuinely clean, free of all those airborne things we don't want? Filtration, that's the absolute first line of active defense inside a mechanical ventilation system. The LEV5 standard, pulling directly from ASHRAE, mandates that those central HVAC systems, the ones supplying either fresh outdoor air or recirculated indoor air to the spaces people occupy regularly, they must meet one of several pretty stringent filtration options. The goal is to ensure a high level of air purification. The primary option, and probably the one most people have heard of, specifies a minimum efficiency reporting value, or MERV, of 13. And that's according to HHA standard 52.2, 2017. To really get your head around MERV, think of it as a standardized rating scale. It tells you how good an air filter is at capturing particles of different sizes.
Okay, higher MERV is better.
Generally, yes. Higher MERV means it captures more particles and smaller particles. It measures how efficiently the filter stops things like dust, pollen, mold spores, pet dander, lint, all that stuff from passing through. Now, to put MERV 13 in perspective, the cheap filter you might have in your home furnace, that might only be a MERV 8, maybe even lower. It mostly catches the big stuff like dust bunnies and pet hair.
Right.
A MERV 13 filter, though, that's a significant leap. It's highly effective at capturing much smaller, often invisible particles. Specifically, it's really good in that critical zero point 0.3 to 1.0 micrometer size range. And why is that range important? Well, that's where you find a lot of bacteria, most mold spores, fine pet dander, lint, and crucially many viruses, which often hitch a ride on larger respiratory droplets or aerosols within that size range.
So it's grabbing the really small stuff?
Exactly. Stuff that can cause respiratory irritation, trigger allergies, and potentially spread illness.
Yeah.
To give you a sense of scale, a single human hair is maybe 50 to 100 micrometers thick. So MRV-13 is capturing particles hundreds of times smaller than a hair, things you absolutely cannot see.
Yeah.
This level of filtration makes a huge difference. It significantly reduces the concentration of common indoor air pollutants and allergens. Now, as an alternative to MRV-13, projects can choose to use filtration media that meets an equivalent class of EPM1 50%. This is defined by an international standard, ISO 1689D 2016.
Okay. EPM 150%, what does that mean?
Right. So ISO 16890 is a global standard for testing filter performance. It specifically focuses on filter effectiveness against different sizes of PM or particulate matter. EPM1 refers specifically to the efficiency against fine particulate matter that is smaller than 1 micrometer, the really tiny stuff. So EPM1 50% filter guarantees it captures at least 50% of those very fine, highly respirable particles.
And why the focus on those tiny ones?
Because those ultrafine particles, often from combustion like vehicle exhaust, industrial processes, even cooking smoke, are particularly nasty for our health. Their minuscule size lets them bypass our body's natural defenses. They can get deep into the lungs, even enter the bloodstream. They're linked to systemic inflammation, cardiovascular issues, not just respiratory problems.
Oh, okay.
So this ISO standard provides another really robust option, specifically targeting high efficiency against these smallest, potentially most harmful particles. Beyond those main filter options for the central system ducts, the standard also recognizes and allows for in-room air cleaning systems.
Well, portable air purifiers.
Exactly. Or sometimes they're mounted in the ceiling. They provide highly localized purification, which could be super useful in specific areas with unique needs, maybe a conference room, or for supplementing the central system in places needing an extra layer of protection. And then for really specialized critical situations, there are systems tested for both effectiveness and safety, according to HHA's Standard 241-2023, Section 7.4. That standard focuses specifically on the really tough challenge of controlling infectious aerosols.
Very relevant now.
Extremely relevant. Furthermore, if the goal is broader treating for both particles and gases, like VOCs or odors, then project teams would look for systems tested per ASHRAE 62.1/2022 Addendum N. And just to reemphasize, for that specific, increasingly critical challenge of infectious aerosols, those microscopic airborne pathogens, viruses, bacteria that spread disease, the very latest HHRE Standard 241-2023, Section 7, provides really rigorous specific testing protocols. It's all about ensuring these advanced systems are truly effective at reducing the risk and protecting public health.
Wow, that's an incredible list of specialized standards and filter types. It really highlights the level of precision needed today. But why are these specific testing standards, especially the ones for infectious aerosols like ASHRAE 241 and the ones for particles and gases, why are they so crucially important right now? Maybe more than they used to be. What's really at stake if these aren't applied rigorously?
They're crucial because they go beyond just general clean air. They target very specific and often extremely potent threats to our health. For infectious aerosols, well, the recent global pandemic was a stark, undeniable wake-up call, wasn't it?
Absolutely.
It highlighted the critical need for systems that can genuinely effectively remove or inactivate airborne pathogens. HHRE 241 was developed precisely for that reason, to provide a robust scientific way to verify that these systems actually work as advertised. This ensures they contribute meaningfully to public health, to safety, to resilience, not just providing, a false sense of security or some kind of placebo effect.
Right, you need proof.
You need proof. If these standards aren't rigorously applied, we risk creating environments where airborne diseases can spread much more easily, impacting people's health, their productivity, even the ability of essential services to keep operating. And similarly, for particles and gases, that Addendum N ensures that systems designed to tackle often invisible threats, things like formaldehyde off-gassing from furniture or ozone or specific industrial pollutants, are properly tested and proven effective. The stakes are really high. Unaddressed gases can cause immediate symptoms, headaches, nausea, or contribute to serious long-term issues like respiratory disease, even cancer. So this level of specificity, this independent verification, it's absolutely paramount. It ensures that the building's invisible shield against this whole range of contaminants isn't just there, but it's demonstrably effective. It's reliable. Maybe a simple analogy helps. Think of a basic, cheap furnace filter, like a very loose fishing net. It catches the big fish, right? A MERV 13 filter, or an equivalent ISO-rated one, is like a much finer mesh net. It catches not only the big fish, but also many smaller ones, even the tiny shrimp and plankton that can still cause problems if they get through.
Good analogy.
So this means the air you breathe in these buildings is being actively scrubbed, cleaned of a vast array of harmful pollutants, even infectious agents. It's a critical, evolving step for protecting public health.
Okay, it's one thing to meticulously design a system. You've got the right ventilation rates, these advanced filters. But how do we actually know it's working? Day in, day out. Is it consistently delivering the amount of fresh, clean air it's supposed to? The standard mentions requiring outdoor airflow measurement devices for larger systems. What does that mean in practice for the building's operation and for the people inside?
Right. If we connect this back to the bigger picture, this requirement is fundamentally about accountability. It's about verification, and it's about optimized performance. For those mechanical ventilation systems that have an outdoor air intake flow greater than 1,000 cubic feet per minute, which is about 472 liters per second.
Okay, 1,000 CF-meter. How big a system is that, roughly?
Well, 1,000 CF-meter is roughly enough air for maybe 50 to 100 people, depending on how dense the space is and what they're doing. So, yeah, we're typically talking about medium to large commercial buildings. Schools, office blocks, maybe large common areas in apartment buildings. For systems that size, these sophisticated measurement devices, they aren't just a nice to have, they are absolutely mandatory under LEED BD+C.
Mandatory, okay.
And this continuous measurement is critical for several really compelling reasons. First, and most importantly, it gives you real-time assurance. Proof that the system is actually operating exactly as it was designed, delivering the necessary volume of fresh outdoor air needed to effectively dilute and flush out those indoor contaminants. Without measurement, let's face it, building operators are basically just guessing if the building is breathing properly.
Right, flying blind.
Pretty much. Second, it provides invaluable data for the building operators.
Yeah.
For proactive system maintenance, for rapid troubleshooting. If, for example, the measured airflow suddenly drops way below its target, that could immediately signal, hey, maybe a filter is clogged and needs changing. Or maybe a fan isn't working right, or there's a blockage somewhere in the ducts. It allows for quick action before the air quality really suffers. And thirdly, it's actually crucial for energy efficiency. If you deliver too much outdoor air, well, the building is just wasting energy heating or cooling all that extra air. Higher running costs, bigger carbon footprint. But if you deliver too little, then you compromise air quality, which directly impacts people's health and productivity. So these measurement devices create this essential continuous feedback loop. They empower the building operators to rigorously monitor, fine-tune, optimize performance. And for you, the listener, this means the lungs of the building you're in aren't just assumed to be working. They're actively monitored, ensuring they're always breathing in the precise right amount of fresh air for you, consistently, reliably, guaranteeing a healthier indoor environment.
Okay, now we're shifting focus quite significantly. We're moving into what our outline calls specialized environments. Specifically, we're going to deep dive into healthcare first and then residential spaces. It seems logical, right? Certain spaces, maybe because the people in them are more vulnerable or because of the critical activities happening there, they just demand even higher, more meticulous levels of air quality. So what are the specific requirements for healthcare spaces under these LEED standards, and what makes them so incredibly stringent compared to, say, a standard office building?
Yeah, what's truly fascinating and frankly vital here is the profound recognition of unique vulnerabilities in healthcare settings and the critical, sometimes literally life or death need for absolute precision.
Sure.
For healthcare spaces, the requirements, they escalate dramatically, unequivocally. They mandate strict compliance with Section 6 through 10 of ASHRAE Standard 170/2021.
Standard 170, okay.
And that's not a suggestion. It's a non-negotiable directive. This standard, ASHRAE 170, it's meticulously tailored. It's exclusively dedicated to healthcare facilities. It acknowledges that these environments have this unique combination of challenges. You've got high-risk scenarios for infection transmission. You've got immunocompromised patients who are extremely vulnerable to even low levels of contaminants. Plus, you have the absolute necessity to protect sensitive, expensive medical equipment from dust and airborne particles. So ASHRAE 170 addresses pretty much every conceivable aspect, from highly stringent pressure relationships between different rooms.
Pressure relationships, what does that mean?
Right, so for example, maintaining negative pressure in an airborne infection isolation room. That pulls air into the room, containing infectious aerosols inside, preventing them from escaping into corridors. or conversely, maintaining positive pressure in operating theaters or sterile compounding pharmacies. That actively pushes air out, preventing contaminants from getting in.
Ah, okay.
It's critical engineering. It also specifies incredibly detailed filtration requirements for different types of patient care areas. Exceptionally high ventilation rates, often measured in air changes per hour, or ACH, in critical zones like operating rooms, emergency departments, rigorous controls for sterile processing areas. The fundamental goal here is multifaceted. It's about dramatically minimizing infection spread, rigorously protecting vulnerable patients from environmental contaminants, allergens, and ensuring the safety and long-term health of the dedicated healthcare staff working there. The sheer stringency of these requirements, it's a direct, proportional response to the life or death implications air quality can have in these uniquely sensitive settings. It's literally engineering for survival.
It's hard to overstate the level of care needed there. It directly impacts patient safety, recovery, just incredible. But now let's bring that same level of detailed thought home, literally, to our living spaces where we spend so much of our time. What are the specific provisions for dwelling units for homes, apartments under LEED BD+C, and how are these designed to make our homes not just, comfortable, but genuinely healthier, safer places to be?
Yeah, this raises such an important question for all of us, right? That directly impacts our daily lives. What does truly healthy air mean, not in a hospital operating room, but in our own kitchen or bedroom? The residential provisions in LEED BD+C are remarkably detailed, surprisingly comprehensive. They ensure that each individual home or apartment meets this rigorous, holistic set of requirements. And again, it goes way beyond just general comfort. It's about specifically proactively addressing those common, often overlooked issues we find in homes. We're talking crucial things like effective moisture control, preventing mold growth, safe management of combustion byproducts from furnaces, water heaters, stoves, and diligently removing that buildup of everyday indoor pollutants from cooking, cleaning, just living. Ultimately, it's about creating genuinely healthy, safe, and resilient home environments for families.
Okay, first up in the residential section, the dwelling unit mechanical ventilation. This sounds like a big shift from just, cracking a window when things feel stuffy. What exactly does ASHRAE 62.2/2022 require here? Sections 4, 6.6, 6.7, and how does that translate into a healthier place to live?
This is absolutely foundational for achieving good residential IAQ. And yes, it represents a significant paradigm shift away from relying on passive, often totally inadequate ventilation methods like opening windows or just hoping for air leaks. Each dwelling unit, each home, each apartment is now explicitly required to have a dedicated mechanical ventilation system designed meticulously to bring air directly from the outdoors. And crucially, the standard emphasizes supply and balanced systems. Let's break that down. A supply system actively brings in fresh outdoor air. A balanced system simultaneously ensures that an equal amount of stale indoor air is exhausted out of the home.
Equal amounts in and out.
Exactly. This balancing act is absolutely vital because it prevents uncomfortable and potentially problematic pressure imbalances inside the house. Without it, you could get weird drafts, uncontrolled air leaking in from places you don't want it to, like dusty wall cavities. Or, more dangerously, you could run into issues with combustion appliance venting, where harmful gases like CO get pulled back into the living space. Yeah, not good. So the goal here is to provide a continuous, controlled, consistent supply of fresh air, without relying solely on opening windows, which is just too inconsistent. Depends on weather, security, noise, outdoor pollution levels.
True.
Now, ASHRAE 62.2 does have some very specific, narrow exceptions for certain super airtight, very small units. But the default, the strongly preferred approach, is active, intentional, balanced mechanical ventilation. This rigorous standard ensures a constant controlled exchange of air in your home, actively combating stale air, diluting pollutants from cooking, cleaning products, reducing CO2 buildup, moisture, bioeffluents from people. It's engineering a continuously refreshed environment.
Okay, we all know kitchens and bathrooms. They're notorious hotspots, right? Generating moisture, odors, cooking fumes, steam, cleaning chemical smells. What are the specific non-negotiable requirements for the local mechanical exhaust systems in these particular zones?
What's really key here is the explicit, uncompromising focus on source control, meaning tackle the pollutants right where they're generated before they spread. So every single kitchen and every single bathroom, including half baths, powder rooms, must be equipped with dedicated local mechanical exhaust systems, and they have to rigorously comply with ASHRAE 62.2/2022, sections 5 and 7. And this point is absolutely critical. The exhaust air from these fans must be ducted to terminate directly to the outdoors. Period.
Directly outside, not into the attic.
Definitely not into attics.
Yeah.
Or crawl spaces or those interstitial spaces between floors or in walls? Absolutely not.
Why is that so bad?
Because exhausting moist, pollutant-laden air into an attic, it's like creating a perfect petri dish for mold and mildew. It can degrade your insulation, rot the wood structure, and eventually those same pollutants and moisture find their way back into your living space anyway, totally defeating the purpose.
Ah, okay. That makes sense.
This provision also means those common recirculating range hoods, the one that just have a little filter and blow the air back into the kitchen, or those over-the-range microwaves with a built-in vent.
Yeah.
They are not considered adequate. They don't count as primary kitchen exhaust under this standard.
Really? Why not?
Because while they might capture some grease and maybe larger particles, they fundamentally fail to remove the gaseous pollutants generated by cooking things like carbon monoxide, nitrogen oxides, formaldehyde from gas stoves. And they certainly don't remove the moisture or the heat. They just blow it back into your face.
Huh. I never thought about that.
So when you're cooking dinner or taking a hot shower, these required properly ducted exhaust systems. They're designed to whisk those cooking odors, the grease particles, the shower steam, directly and completely out of your living space, preventing them from spreading, keeping your overall indoor air much cleaner. It's about a clean break from those indoor contaminant sources.
Okay, direct exhaust is key. Got it. But what about those really powerful kitchen hoods? You know, the big stainless steel ones that sound like a jet engine. I think you mentioned something about makeup air being needed for those. Why is that necessary? What happens if you don't have it?
Indeed, that's a very important point. If a local exhaust system, especially one of those high-capacity kitchen range hoods, is capable of moving more than 400 cubic feet per minute, that's about 188 liters per second, quite a lot of air,
Okay, 400 CF meter.
then a dedicated makeup air system becomes absolutely mandatory. It's not optional, it's essential. Because a fan that powerful can rapidly and severely depressurize your home. It's pulling a huge amount of air out.
Depressurize, meaning it creates a vacuum effect.
Sort of, yeah. A negative pressure. Significantly more air is being pulled out than is coming in naturally through leaks or other openings. And this imbalance, it sounds minor, but it can cause a whole cascade of problems. It can suck cold outdoor air in through every tiny crack and crevice around windows, doors, electrical outlets, creating uncomfortable drafts, jacking up your heating bills. It can pull air from places you really don't want it from, like your garage, hello, car fumes,
Right.
or a dusty attic, or a damp crawl space, bringing in odors, dust, maybe even radon gas or mold spores.
Oof.
And perhaps the most dangerous part, especially in homes with gas furnaces, water heaters, or fireplaces, it can cause backdrafting, where that negative pressure literally pulls dangerous combustion gases, especially carbon monoxide, the silent killer, back down the chimney or flue and into your living space instead of letting them vent safely outside.
That sounds incredibly dangerous.
It is. Extremely dangerous. So, to counteract these serious risks, a makeup air system is designed to actively bring in an equal amount of outdoor air whenever that powerful exhaust fan is running. It keeps the pressure inside the home balanced. These makeup air systems, they have to be automatically controlled, meaning they switch on and off right along with the exhaust fan. And crucially, they also need a means of closure, like a damper. So they only bring in unconditioned air when the fan needs it. They don't just leave a hole open to the outside all the time, wasting energy. This careful design keeps your home's pressure balanced, prevents all those problems, while still letting you have that powerful fume extraction right when you need it, like when searing a steak.
It's clear there's a lot of thought going into balancing air exchange and avoiding those pressure problems. And for bathrooms specifically, I think you mentioned there's a strong focus on energy efficiency too, right? Is that just about remembering to turn the fan off, or is there more to it?
Absolutely. The focus on energy efficiency for bathroom fans is quite significant now. All bathroom exhaust fans are required to be Energy Star labeled, or show equivalent performance if the project is outside the U.S.
Energy Star, okay.
And this requirement, it's not just about saving a few cents on your electricity bill, although it does that too. Energy Star fans are designed to be not only highly effective at their main job, removing moisture and odors, but also remarkably energy efficient and, critically, often significantly quieter than older, standard, noisy fans.
Quieter is good. Those old ones can be loud.
Exactly. And the reduced noise is actually a subtle but important feature. Because if the fan isn't annoyingly loud, people are much more likely to actually use it consistently.
Wow.
And run it for longer after a shower, which is crucial for proper moisture removal.
Good point.
So it directly leads to better moisture control and healthier air just by being less annoying. But for an even bigger leap in efficiency, especially if you live in a climate with very cold winters or very hot, humid summers, you can incorporate a heat recovery ventilator, HRV, or an energy recovery ventilator, ERV.
HRVs and ERVs. How do those work?
Okay, these systems are incredibly clever. A real advance in residential ventilation. They provide that balanced mechanical ventilation we talked about, bringing fresh air in, exhausting stale air out. But here's the magic.
Yeah.
While doing that exchange, they simultaneously transfer heat, or in the case of ERVs, both heat and humidity, from the outgoing stale air to the incoming fresh air in winter, or vice versa in summer.
So they recycle the energy.
Precisely. They recover that thermal energy. This dramatically reduces the energy loss that normally happens when you just exhaust your nice warm indoor air in winter and bring in freezing cold outdoor air, or dump cool dry indoor air in summer and bring in hot sticky outdoor air. HRVs mostly focus on transferring heat, great for heating-dominated climates. ERVs transfer both heat and moisture, hugely beneficial in humid climates as they can help manage indoor humidity levels effectively. And to qualify for LEED V5, these HRVs and ERVs need to meet the stringent Energy Star technical specifications for residential HRVs, version 2.3. This ensures they are both exceptionally effective at providing continuous fresh air and highly energy efficient. It basically lets your home breathe in the most efficient way possible, cut your energy bill significantly while maintaining top-notch indoor air quality and comfort. It's really a win-win.
Okay, moving beyond just moving air around. There are some incredibly strict rules about how we safely use fire and gas appliances inside our homes. This seems critical for safety. What are the LEED B5 requirements around these combustion appliances? Why are these specific dangers addressed so rigorously?
Yeah, this touches on an absolutely paramount issue: safety from within the home itself, addressing those potentially invisible yet possibly lethal threats. First, and this is a big one, cannot be overstated: unvented combustion appliances, with the only exception being standard cooking ovens and ranges, are categorically not allowed in LEED V5 certified homes.
Unvented appliances, what exactly are those?
We're talking about things like unvented gas fireplaces, those decorative gas logs that burn without a proper chimney, or maybe unvented gas space heaters. Appliances designed to release their combustion byproducts directly into the room you're in.
Okay, so no vent to the outside.
Exactly. And this prohibition is a critical, life-saving safety measure, because these types of appliances produce a nasty cocktail of pollutants: carbon monoxide, CO, various nitrogen oxides, and NOx, fine particulate matter. Without a direct, sealed exhaust path to the outdoors, these hazardous byproducts can very quickly build up to unhealthy, even lethal concentrations inside a home, posing a severe risk to everyone inside.
And to further guard against these hidden dangers, especially carbon monoxide, you mentioned CO monitors are now mandatory, even in homes that don't have those specific unvented appliances. Why the universal rule?
Precisely. This is a crucial, non-negotiable safety layer. A carbon monoxide monitor must be meticulously installed on each floor of every single dwelling unit. And importantly, they must be hardwired with a reliable battery backup.
Hardwired plus battery. Why both?
Hardwired means it's connected directly to the home's electrical system, ensuring continuous power. The battery backup is the essential fail-safe that keeps the monitor working even if the power goes out, which is often when people might resort to unsafe heating methods.
You are a good point.
And yes, the requirement is universal, mandatory in all dwelling units, regardless of whether that specific unit has any gas appliances or an attached garage or not.
Why everywhere?
Because carbon monoxide, tragically often called the silent killer, is completely invisible, colorless, odorless, tasteless. And it can come from surprising sources. It might migrate into your apartment from an attached garage where a car was left running, or from a malfunctioning furnace in an adjacent unit, or even from a faulty appliance in a common area of the building.
Wow. Okay. It can travel.
It absolutely can. So this universal monitoring system acts as an indispensable safety net against this truly insidious, potent threat, offering continuous, reliable protection for every single occupant. It's an active defense against an unseen enemy.
Okay, now lots of people, myself included, really love the ambiance, the warmth of a traditional fireplace or maybe a wood stove. How does a LEED V5 handle these features? They're beloved, but they obviously involve combustion. How do you balance that comfort with safety?
Yeah, they are indeed still allowed. Their charm isn't dismissed, but they come with exceptionally strict controls to make sure they don't compromise indoor air quality or safety. Any indoor fireplaces and wood stoves must be equipped with solid glass enclosures or doors that achieve an effective seal when they're closed.
Sealed doors. Okay.
This design feature is paramount. It minimizes the amount of smoke, fine particulate matter, and other combustion gunk that can spill out into the living space while the fire is burning, significantly improving indoor air quality, reducing respiratory irritants. Furthermore, and this is a critical safety provision, if these fireplaces or wood stoves are not what's termed closed combustion or power vented.
Meaning they don't draw their combustion air directly from outside and vent directly outside in a sealed system.
Correct. If they rely on room air for combustion and a standard chimney, then they absolutely must pass a rigorous backdraft potential test.
Backdraft test, what does that check?
It's designed to confirm that the depressurization of the combustion appliance zone, basically, the area around the fireplace, remains less than 5 pascals when other exhaust fans in the house, like the kitchen hood or bathroom fans, are running.
5 pascals. How much pressure is that?
It's incredibly small. Think about the pressure exerted by maybe a single sheet of paper resting on your hand. It's tiny. The whole point of this meticulous test is to verify that even under worst-case conditions, the house won't become so depressurized that it starts sucking dangerous combustion gases, CO, smoke, back down the chimney and into the living space.
Okay, so it prevents the chimney from working backwards.
Precisely. It ensures that enjoying that cozy, crackling fire is still entirely possible, but it comes with robust, scientifically proven safety measures, meticulously engineered to protect your indoor air and, most importantly, your family's health. It's about smart, safe enjoyment.
And finally, let's quickly touch on the bigger heating systems. The ones usually tucked away in a basement or closet, space heating furnaces, boilers, water heaters. What are the LED V5 rules for these combustion-based workhorses to ensure maximum safety in the home?
Right, those essential space and water heating equipment that rely on combustion, and that includes many common furnaces, boilers, and water heaters. They also have to be designed, installed, and operated with the most stringent safety protocols. This means they should unequivocally be either closed combustion or have power-vented exhaust.
Same terms as for fireplaces, so sealed systems?
Exactly. Closed combustion, again, means it has completely sealed pipes for both bringing combustion air in from outside and exhausting the byproducts directly outside, totally isolated from the indoor air. Power-vented exhaust means it uses an electric fan to actively push the combustion gases out, ensuring they can't leak back into the house. The highly controlled nature of these systems prevents any accidental release of those harmful combustion byproducts, CO, NOx, particulates directly into the home's air. The only acceptable alternative, if for some reason neither of these sealed systems is feasible, is to physically locate this combustion equipment in a completely detached utility building or maybe an open-air facility, like a shed outside the main house.
Okay, so separate it completely.
Completely separate the combustion process and its potential hazards from the actual living space. This whole approach fundamentally ensures safer heating and hot water, proactively protecting your home and everyone in it from the inherent risks of burning fuel right at the source. It's about building safety in from the ground up.
Okay, we've covered a lot on the air itself: ventilation, filtration, combustion safety. Now let's shift focus slightly, moving from the invisible air to something more tangible, what we track in every single day on our shoes. Our source outline mentions entryway system design. Now, this sounds maybe deceptively simple, perhaps even a bit mundane. But what exactly does it involve, and why is it considered a fundamental, important air quality requirement in LEV5?
Yeah, if we connect this back to that overarching goal of managing indoor air quality, this requirement is actually about the most elemental form of pollutant control, literally minimizing the contaminants that even enter the building in the first place. Stop them at the door. This provision specifies the mandatory installation of permanent entryway systems at all primary exterior entrances. Their purpose is elegantly simple, yet remarkably effective: to capture dirt, dust, sand, maybe pesticides or road salt, other particulates, directly off people's shoes as they walk in.
So like those heavy-duty mats you see.
Exactly. While the LEED standard doesn't actually dictate a specific minimum length for these systems, the clear intent is to establish a robust physical barrier. Think about those long, durable, maybe ribbed walk-off mats you often see in high-traffic office lobbies, school entrances, modern apartment buildings. Or sometimes it's a recessed metal grate system where the dirt and grit fall down into a collection tray underneath, keeping it off the walking surface. It's surprisingly low-tech, maybe, but it's a highly effective passive measure. Significantly improves overall indoor air quality.
How does a mat improve air quality?
Well, by physically removing all that dirt, debris, and tracked-in gunk right at the threshold, you dramatically reduce the amount of dust, allergens, and chemicals that would otherwise get tracked throughout the entire building. This obviously makes for a cleaner-looking environment. but it also significantly cuts down on the frequency and intensity of cleaning needed inside. Less vacuuming, less mopping, fewer harsh cleaning chemicals used perhaps. It could even extend the life of your interior flooring like carpets. And critically for air quality, by stopping those contaminants right at the door, you reduce the overall particulate loads circulating in the air. Less dust kicked up, fewer allergens floating around for people to breathe in, which means less work for your HVAC filters too. It's a simple, effective first line of defense.
That's a fascinating point. It really is a surprisingly impactful detail, isn't it? Directly influencing the cleanliness and the actual quality of the air in the spaces you walk into every day. Essentially creating this robust first barrier against countless outdoor pollutants. Who knew a humble doormat could be so vital? So let's try and wrap this up. What does all of this mean for us, for the people who live, work, learn, and just exist inside these buildings? We've taken a really deep dive today into LEED v5's fundamental air quality requirements for new construction. And what we've uncovered is this incredibly comprehensive, multi-layered approach, all aimed at ensuring the air we breathe in new buildings is as healthy, as supportive, as life-affirming as possible. From that crucial first step, meticulously understanding the outdoor air around the building, through to deploying advanced filtration systems acting as invisible shields, to specialized ventilation strategies tailored for critical places like hospitals, but also for our everyday homes. And even down to that deceptively simple yet profoundly effective entryway mat. Every single detail seems considered, meticulously designed, rigorously implemented, all to create healthier, more resilient indoor environments for all of us.
Yeah, and it's really important to stress this isn't just about architects or engineers mechanically ticking boxes on some checklist. It's not merely about compliance for compliance's sake. This entire framework, it represents a profound, systematic, and constantly evolving commitment. A commitment to occupant health, to holistic well-being. The standards we've talked about today, ASHRAE 62.1, 62.2, 170, 241, that ISO 16890, they are like the unseen architects of our indoor air quality. They're constantly evolving, incorporating new science, new technologies, always working together to create healthier, safer, more productive environments for every single one of us. They ensure that the air, this fundamental necessity of life, is finally being treated with the care, the precision, and the respect it truly deserves.
So next time you step into a brand new building, maybe a new office tower, a school, a hospital, or even just take a deep breath in your own home if it's been designed to these kinds of standards, maybe take a moment. Consider that invisible world swirling around you. Think about the thoughtful design, the cutting-edge technology, the rigorous standards that might be actively at play, tirelessly working to protect your health with every single breath you take. It really makes you wonder, doesn't it? What more could be done, especially maybe in our existing buildings, the older ones, to ensure the air we all share everywhere is truly sustaining, truly vital, actively contributing to our very best health and well-being. If you found this deep dive as invigorating, maybe as clarifying as a deep breath of genuinely fresh air, then don't miss out on our future explorations. Make sure you hit that subscribe button. Join us as we continue to unpack the fascinating, often hidden details that shape our world, shape our health, and ultimately shape our lives.